We'll still talk about the factor of safety, but we'll use a new idea, the statistics, to try to explain how we do things. This is just going back to what we've done so far. The first time we talked about the definition, and we discussed that safety factor 4 was not really what we were doing. Yesterday, we looked more closely at demand and capacity, and I gave some example on designing for worst case load when I was talking about my trailer, and that you just want to be able to lift it up with the wind pressure from driving and still have everything strong enough. And then we talked about the little ATV, discussing that you don't have to put, let's say, welds all around. It's still going to be strong enough in most cases. We didn't talk a whole lot about inspection, and one of the reasons is Professor Eager talked about it and will continue to talk about it. The inspection requirements are different from one standard to the other. When we're looking at ISO, for example, some of their requirements for welds are more specific than what we have with AWS. And I'll just give you an example here. So if I'm an inspector and I inspect with ISO, let's say I have a T connection between two members. It's right here. Well, we'll do it side by side. So if I have, if here I have an ISO weld, I'm going to draw it just like this. It just simplifies my description here. The angle between the two pieces here, we're going to measure it this way from the outside because that's how the standard calls for it. So let's say we call this theta, and we're going to say it's got to be greater than, and then they have three different levels. If it's the lowest quality inspection, they say it's going to be greater than, is it 90 or 100? I'll put a question mark, but it's either 90 or 100. It's not very precise. Then you have 110, and you have 120. The idea is, by looking at it visually, you can determine whether you had enough heat when they welded to fuse enough of and heat up this metal, so the contact between them. Let's say we have a flat surface and we have a bead of metal on it. If the bead is looking like this, that's a cold weld. This is a situation of a cold piece of metal in which you put the liquid metal, and there's a high surface tension between them, and that's why it's bulging up, a little bit like paraffin would do this behavior. Oil on water would do this behavior. It just doesn't want to have too much of that interface between the liquid and the solid. When you heat it up more, the bead's going to start looking like this, and you're also going to have melting of your base metal underneath. And that's what we want for welding. So ISO is very specific about asking for a specific angle from a visual standpoint. It's still not perfect, because if I go out, most of the time this is too small to really put a measuring device. So I have to evaluate visually whether I think that it's a straight out type of weld. So the other standard we talked about, AWS, will allow you to stick out like this as long as overall this convexity is not more than a certain amount. And I'm not, from my perspective, this is even harder to evaluate how much convexity you've got by looking at it visually. But if you hire an inspector, say, come and look at my welds, these are, to be shipped to Europe for this construction project. Well, the inspector should be informed as to he's going to inspect this way or this way. And maybe, maybe he's trained to do only one of them by experience. So inspection also ties into our factor of safety. In the work I've done going around various structures, I prefer looking at the angle. Maybe because I can figure it out personally better. When the issue you have here is if this weld is made out of multiple passes. So if I have, I'm just going to redo this one here, but this time we're going to say it's a bigger member. So somebody came, did the first weld like this, another weld like this, another weld like this. I'm making it up, but you don't have a whole lot of convexity. But if you have something that exactly like I drawn that's actually pushing this way, that's also unacceptable by AWS. You can't have the weld with an angle less than 90 by AWS as well. But if you're exactly at 90, all you can do with AWS is use the criteria, the subjective criteria that there's a lack of fusion. And it's the case, and people will do it. They'll say, hey, no, this is not a good weld. It's not acceptable because I believe you don't have the fusion. But it's a more qualitative description than saying, well, you're on the edge, you got 110 degrees, or you got 100 degrees, or whatever the number is from your estimate. So this allows to quantify, and that's another topic that Professor Eggers taught us in this class. If you can't quantify a lack of fusion, how can you really control it? Somebody is going to say, well, it's borderline lack of fusion, or it is lack of fusion. Typically, when it's a quality control inspection, it's a go, no-go criteria. But if you are building a lot of a certain type of structure, you can also go back and figure out, in general, what your welds look like. If you came out and say 90% of the time they're 120 degrees, but 10% of the time they are 90 degrees, well, that tells you you can't rely on a single connection to be fully reliable, because when you go to 90 degrees, this type of situation, you don't have ductility typically. When you're not fused, so this is a situation where fusion will be very limited under these beads. There'll be a little bit maybe in the middle of the bead. Whereas on a weld like this, you expect to melt this whole area to make the connection. So I just thought in terms of when we were talking about the capacity, I'll mention the inspection as being a specific aspect to call for when you're making a design. When we talked about this, if you just ask for a weld, you get a weld. Sometimes people will say, well, I want a half-inch weld. Well, this is a half-inch weld. This is also a half-inch weld. Maybe this is a 1-inch weld. Is it okay also to have a 1-inch weld, but that's not fused? So this is where it comes in to say, well, you got to do it by ISO. You got to do it by AWS. The Joist Institute also has some welding requirements. ASME has welding requirements, and they're all different. The AWS is the only one that you don't have to qualify a single weld. If you say I want this very typical type of welding detail, as long as you have a qualified welder and a material that is listed in AWS, you can go and weld it. So that's a big advantage as opposed to the other codes. They will require you, even though your joint is very simple, to do your own qualification. So qualification, I think, is just part of the specification, and it does, and when I was talking, for example, yesterday about the ATV, whether it's okay to have welds that are not good all around, that comes into qualification testing. You hope that in qualification they do it all well, and then you may say, well, because I'm using some robots and the setup may vary a little bit every once in a while, but maybe I have a weld out of the 4 all around. That's not going to be fully fused. So now you know when I say not fully fused, that's what I mean. I mean a bead that's going to be more like a caulking joint here in the corner as opposed to being flatter like this one. And it's all based on the fusion. So the inspector needs to be told or needs to know what's acceptable and not acceptable in addition of being there. So we have a lot of different things that ties into the factor of safety. We did cover these. So design with the trailer specification, that's what Professor Eager is talking a lot about in this class. Manufacturing, well, there's some variation when we're talking about welds, and that needs to come into account in the design. We talked about the trailer where we wanted to put the welds away from the highest loaded locations, specifically to rule out manufacturing as affecting the strength. There's still the manufacturing of the wrought steel itself, but that really tends to be consistent as opposed to making bolted connection and making welded connection. Another example here of things that are not accounted for in the design, it's a pressure vessel with a factor of safety of 4. And what happened is on the inside, they had a rubber seal in the bottom. So the rubber was at the bottom and making it up a certain way up. With the intent, we think, we don't know the intent from the designer, but one advantage of doing this is you can reduce the exposure to oxygen. You can reduce also the temperature of exposure for the metal. You can hide a welded connection that may not be as corrosion resistant as the cylinder itself. Now, and it's the region where you have the most hydrostatic pressure, just from gravity. So they had an overpressure, and they found at the very end that the crack was unzipping around the circumference, which in principle is the direction that you only have half the stress. But what happened is the crack somehow knew that it was being sealed. So the crack grew all around with the rubber bridging it so it didn't leak. And that's a concept that I remember when I was a student, the professor said, well, leak before break. Okay, so I said, fine. How exactly do you do that? Because I was not exposed to it. Everybody knows what leak before breaks mean? You do? Yeah, everybody. Good. All right, we're not going to draw it. So you want to be able to sustain a crack that grows through the thickness and allow for a leak before you reach the fracture toughness, where the crack just unravel. So you allow for not critical crack growth. So subcritical, it's growing by fatigue or creep to a point where you go through the thickness and you start leaking, and people know that there's a problem, and so they have to come and fix it. As opposed to blowing, say, you start growing a crack up to 90%, and I've seen it. So say we have a vessel, and we're looking at it from the top down. This would be like the same similar structure as this. We're looking down, and well, I'll say it's from the inside because of some chemicals. There's a crack that grew like this, a semi-elliptical crack. That creates this stress intensity at the front of the crack here. And what you want is, given your thickness, you require the material to be tough enough so the crack can actually grow all the way through, like this. Leak. and people react to it and fix it. So the main requirement is not based on the fatigue resistance. It's only based on the fracture toughness of the material, and that's that K value. That's related to the stress square root of pi A. A is the length of the crack here. And then we can add a little fudge factor here. So the idea is, for a given application, you want A to reach T, giving you a level of stress, and all of this be inferior to the toughness of the material. There's really, and then you can say, oh, I want it to be, a certain size. Now, when you come up with all of this, you're assuming that the crack is not going to seal itself. And that wasn't the case with this vessel here because of that rubber membrane that was in there. We have projects where we see copper pipes that have holes that go all the way through the thickness by pitting corrosion. And they seal themselves. Say if it's a hot water, you have a little bit of flow. All the salts and maybe some organics from the water just come through the crack and seal it. So what are you going to do about this? Are you going to also be inspecting for stain? Because most of the time it is visible, but as a stain, a white stain as opposed to a leak. In this example, and that's a bit the idea, why I put it in the first place is, if you're looking carefully at the bottom of this pressure vessel, you'll see the rubber. You were probably able to see the rubber before it cracked. But was that type of structure subject to an in-service inspection? Most of the time, it's not really. There's no necessary visual inspection schedule. Well, it depends on the type of factory, but in some factories, they wouldn't have anything very specific to look for little bulges of rubber or stain coming from a leak that's opening and sealing. So it comes back to this idea that you don't design with a factor of safety that's minimal, thinking, oh, it can break, it'll be fine. So you have redundancy in your safety. You don't want it to get into this leaking situation. If it happens, you hope that inspection's going to catch it, or that it will actually leak and relieve the pressure. And there's nothing perfect. It just becomes a question of acceptable risk. And the reason they were able to do this for a while is they thought, hey, it's going to improve our design. And when they start getting some feedback like this, I'm sure they had to move back and say, well, we'll let it corrode and leak. It's just safer. So that's where the history comes in. So I think you have the idea, as far as design and manufacturing, how you can affect your factor of safety in different ways. So we're going to go ahead with the statistics for today. And the statistics typically work backward. And that's something that we've discussed. And if you try to come up with a new design and you want to do a statistical design, I'm sure you can. Is that going to be very helpful to you? Probably not. It would be only helpful if what you do is you look back to a similar application and find out how they consume the factor of safety by experience, how they design it very precisely, and what's their failure rate, and what is it attributed to, as opposed to just saying, well, I'm going to assume that the material properties are going to be plus or minus 20% of typical value. Okay, so where did that come from? I mean, you need to have a basis for what you're putting in, and that's why it's easier to do it after the fact, and that's why it's very hard to start from scratch with a very optimized design. You know, when Honda started to do these little ATVs, they were clearly over-designed. They were much stronger and much more long-lasting than they probably wanted them to be as well. But they wanted to penetrate the market, and they didn't have the history of all of this being used everywhere. And they were somehow able to afford it. So they went on with a design, everything. I mean, the exhaust system, just things would just last forever. And they changed. So they just went back and started to optimize based on the history. So I don't want to create here this false idea that you'll start from scratch, take some notes, and go to some handbooks and come up with a statistical design for your new product. You can do it with an existing product, and that's a little bit more what we're going to be doing for the next 20 minutes or so. So this is just a normal distribution for a failure where things will fail after a mean amount of time, and then there will be things that will fail prematurely for various reasons or at a lower load, and things that will last longer. It's very easy when you think about a simple parameter. So here we're looking at it in 2D, and you probably remember 1 standard deviation, 2 standard deviations. So if you are away by 1 standard deviation, 60-something% of your failures are going to be within that range, plus or minus 1 standard deviation. So that's a little bit what this shows here. This is the reference that I'm using for the statistical discussion. It's not a book that you're going to go again and design something new with it, but it's helpful to understand why people do the things the way they do. So we talked about demand and capacity in the last class, and here we have it in an X and Y plot. There's some uncertainty on each, and that's why our design, our overall design, our manufactured structure or product is going to behave in a certain way where most of the time it's going to be here away from that failure boundary that you have at 45 degrees. But as you change your conditions of what it's being exposed to outside the precise value that you've put on your design, that's where your safety factor goes down and you get close to that failure boundary. And in this case, they overlap here on the last circle. So there'll be a given combination of load and strength that will result in a failure. I'm sorry? They're just saying that this probability of failure is constant around that circle. And that's just assuming that each parameter is working on the positive side and the negative side in the same way. And we have a circle because we're assuming that we have, say we have a 20% variation in capacity, and we have a 20% variation in demand. It's not the general case. If we look at this, maybe one thing to keep in mind is, in the case of a worst case scenario, based on this, if I go pretty bad just on the design, I'll still be okay on the capacity side. I'm sorry for using the design. So on the capacity side, here, if I'm changing the load applied, same thing. But when there's something that was not what I intended as a nominal value, both ways, that's where we have the failure here at an angle in the chart. And it doesn't have to be straight, so that's why now we look at it in 3D. It's still the same thing where we have the demand and the capacity, and this cut is at an angle here. for the failure. This is more or less saying, and I think it's probably fair, that you can break just about anything. Everything that's being built and is being sold can be broken, one way or another. Sometimes because that specific one was not exactly as strong as the others. Sometimes it's because you just put too much load on it. So that concept is almost universal. And what we're going to go through is see how exactly after the fact we can determine that's probability of failure. The criteria for being in that zone here, this looks big, huh? But it depends you looking at it over what period of time. If you look at it when you get a product right off the factory, this looks big. But if you look at it at a probability of failure over 10 years, maybe for an aircraft it's 20 years, every day something happens. Every day there's a different load. Every month or year they do significant repairs on your structure. And that's where, the cut in the pie would probably start very close to zero here when it's coming out the factory. And then as time goes, it's just going to creep up on you. And that's taking into account in this basic criteria here where you have a multiple factor. So you have time that's coming in, or frequency that's coming in, and then you have for various structure this social criterion factor. So what it says is if you're looking at something that a lot of people would be exposed to a failure, like a dam, you want to minimize even further your risk. If you have 2,000 people on a bridge, it's not like my tire blowing up because it's a hot day and I wasn't parked at the right location or something like that. Now, these factors, when we're looking down here for towels, masts, and offshore structures, I think the offshore structure is really true. When Hurricane Katrina, when some of the Gulf storms come in, it's not atypical to have a whole platform just collapsing. Now you hope that before they do it, they're able to shut the well, but the basic idea that it's out there, there are very few people exposed to it, it's worth a lot of money, but it becomes more of an economical decision rather than a people's safety decision. When we're looking, like the Longfellow Bridge just across here is more than 100 years old. And if there was a risk for it to really fail, well, we'll have to shut the red line and get it fixed. Because there are a lot of people that count on it every single day. Just the train going on it is different than a few cars and bicycles every once in a while. It's creating the highest loads and exposing a lot of people at the same time. So it's a little bit how they in the book go about figuring out why people do things a certain way. If we're looking at a bridge, I thought when I looked at this that the factor for a bridge was not that high. But it really depends on how many people are going to be exposed, how many cycles you're going to be having, and if we're looking at a short-term risk of failure or a long-term risk of failure. So here we are with the question, I would say, of time, because this shows like a different probability, but I would think of this as being, if I start here, so let's say I want a factor of 2 to begin with, and I'm only going to be loading it as it gets off the factory. I do some pressure test, I think it's really good. Going to load it, say 100 times or 50 times, whatever the number is, for the first few months. As time goes by, these little probability here are going to become more and more important. And I specifically picked the factor of 2 of initial safety factor. This is what they call a stochastic safety factor. So the real factor of safety comes down to about 1.2. So that's taking into account probably some maintenance, some inspections, some variation in loads that were not expected. In case of a bridge, bigger cars, smaller cars, more salt on the road, more lanes, you don't really know. You don't really know what's coming up with a bridge. And that's why you put a safety factor to begin with also. But that safety factor becomes significant when you, if we have this distribution, I'm going to draw it. It's the normal probability distribution. So it will look like this. And I'm looking at it for 5 years first. So say for 5 years, and this becomes, say this is 3 times the standard deviation. So at 3 times the standard deviation, we're still, and we put the 6 sigma here. You heard of 6 sigma, right? So this is something that I could probably test for if I really wanted to with my design. This is something that I would very hardly test for in practice. The way I get here is by inferring that I've done my job, up to the certain interval that I was able to. And that's where these probability and the risk and your factor of safety is changing. When you change between something you can measure, you can predict this by testing, or maybe you just do 1 sigma. A certain value here you can test. There's a certain point where really it's not practical. And the only way you can do it is by looking at the history, and from this plot, thinking about that if I start with a factor of safety of 2 based on what I know, I end up with 1.2. And I think you'll keep that in mind if you just go on the drawing and try to start something from scratch. If I'm looking at my trailer, well, I'm not planning to sell it, okay? So as far as user and knowledge, it kind of stays with me, and it's going to go for recycling one day, probably. If we're looking at a bridge, well, the designer is not even going to be there 30 years down the road. And whoever is going to start making decision may or may not know everything that came into the original design. It may make some decisions, like throwing salt. I worked on the bridge collapse in Minneapolis, so I'm only talking about it in a very general sense. But you can think of somebody says, oh, the bearings to hold the piers are locked. So that bridge, we talked about expansion in the first class, going back and forth. Well, a bridge is a good example. The bridge is going to want to move if it's a metallic bridge between seasons. Now, if the inspector says, well, I think the bearings are locked. It's been there for 40 years. It kind of makes sense. And, doesn't necessarily make a whole lot out of it. It's not, they don't say, well, we got to bring the firefighters to throw some grease in here and make sure that it starts moving again. Then your factor of safety is going down. Is it going down 10%, 20%? See, our margin has become lower already. And depending if you assume there was going to be maintenance, at that day, after 40 years down the road, it makes a difference. And obviously, you hope that within 40 years, people will go back and look at your design and try to figure it out, whether you were conservative or not. But it's not always the case, and that's why the code looks very conservative. the bridge building code looks very conservative. There's a safety factor of 2, but then you also take the low material properties into account, and they have some criteria figuring out the load and the wind load, and it's got a lot of complexity built into it. But in the end, they still don't want to make that bridge twice as heavy as it needs to be. It's just not the case. It's already very heavy. I remember going through some numbers to realize that 80 or 85% of the load was the dead load on the bridge. And everything with the cars and everything you can think of is just 10–15%. So it wasn't a whole lot of fatigue. There was some fatigue, but from my perspective as an engineer, it was more loads that were not necessarily taken into account, or things that were not taken into account in the design in the first place. And it's very hard to go back. It's always easy to go back and say, hi, right here, you know. But, and that's why the code has some built-in factors, and that's why time in this case doesn't really affect the intrinsic strength of your design. So maybe when we're looking at this, it's more a question, when are we going to hit our highest load? In the case of the bridge in Minneapolis, it was the hottest day of the summer with construction load on it that was offset at the location where maybe, you know, from a design perspective, things were not exactly the way they were supposed to be, according to NTSB anyway. So yeah, it just took 40 years to get there, but it happened. And then if you take any one of those variables out, I guess you wouldn't have a problem. You take the construction load out, it wouldn't fail that day. If it wasn't a hot day, probably it wouldn't fail that day. If it didn't have the lock bearings, well, you know, probably it wouldn't fail that day either. So it'd be able to accommodate more. Locked or partially locked. So I mean, anyway, there's a lot that comes. It's really sad when you realize, oh, we reached 1. That's what failure analysis is about. We reached a factor of safety of 1. We failed after so long. But there's something to learn from it, and that's where all the history comes in. That's where that's why we have a framework for how exactly we're going to do the demand and how exactly we're going to do the capacity. And as long as that works, if you're going to change something, you better know what you're doing, because if you don't know, if you start really on a 2 curve and how low you need to go in probability, that's more or less of a, it's not 6 sigma, but it's pretty much very low probability that we're looking at down the road. But for certain applications, it's acceptable. Like I like this one here. Let's start at 1.2. If you don't change your landing gear components on an aircraft, it's going to fail eventually. So you could say that for a very long life, it's built with a factor of safety of 0.6. So it all depends how you look at it. And I think you get that idea by now. So we're going to go through 2 little examples. Helicopter blades. This is something I worked on. They were arguing essentially intellectual properties. Somebody was trying to copy somebody else, and the question was their design, to us, was their design good enough or as good? Because there's a lot in reverse engineering in aerospace. You have to show as good from every standpoint. Otherwise, you have to do it a full qualification on your own, which is very difficult, because it means a lot of actual up-in-the-air testing and analysis. So you typically only have 2 of these blades. So we start with the rotor in the middle, and it comes out. It's got a front leading edge and a tail. When you get to the rotor, you have a bunch of stiffener, because that's where your highest load is. The reason it's the highest load is all the centrifugal force that's pulling on the end of this way. we're not doing all the way to the end. Let's say we're doing relatively close to the rotor. So we're going to make the rotor a little bigger here. So we're close to it. It's a tapered section. Say we've identified one of the region of highest load. The centrifugal force, well, it's the rotation speed. So we can get a good estimate from that, based on everything we know about the design, how much aerodynamic, the force of the engine. So say we come up with a maximum value for that. Now, we also have the wind pressure and the rotation direction that's really strong. And it's one of the reasons why this wing, this blade is deeper in this direction than in this other direction. But you do have the uplift force also. That's what keeps the helicopter up. And that's fighting against the thinnest direction. So by looking at this, we were talking in the trailer example about a soft point. I know my highest tension is going to be right here under the thing. It's going to be in this direction, coming from both the traction on the blade and the bending from the uplift. And we can probably take also, maybe it's a little bit to the front because of the bending from this rotational moment. So we've already, narrowed down what we're looking at. And we can go and start putting strain gauges and find out precisely, or run computer calculation to find it out precisely. Now, what it means for the design is this front here is all aluminum. And they call it the Spar. And then when you get to the trailing edge, it's compression. It doesn't resist much bending. It's a smaller section. It's more compliant. So this is more for aerodynamic effects that it's there, as opposed to really like strength perspective. And therefore, it's made out with a honeycomb core, and it has an aluminum skin. So if we go and decide, I'm going to change the aluminum from this front section. So if we're looking at this, what I want to do is make the front out of an aluminum alloy, because it's more reliable. Let's just be very clear on that. And then the tail is going to be some form of a composite structure, honeycomb, anything you want, silver foam. And we're looking at a very high tension somewhere in that area. So this is an extrusion. We're going to be looking at the properties of that extrusion for a crack that will run transverse. It's actually the direction where you have the highest strength from extrusion. If you were looking at a crack that would go this way, it would go a little bit between the laminar levels of the grain structure of the aluminum. So we can go and start looking at the material properties, specifically in this case, fatigue properties, although this is essentially exposed to the environment. So if there's any risk of an effect from salts into stress cracking, we also need to test for that. So if we have two alloys and we want to verify that the new one is as good, we're looking for stress corrosion cracking. I'm going to look for ice cycle fatigue, and that's the plot we had yesterday from the SN curve, where over time the strength's going down. So that's also a factor why our safety factor is going down with time. And we may be also looking at fatigue crack propagation. That's the rate by cycle that the crack's going to move in if it starts penetrating. Now, I should say right now that some of the designs will allow for this to happen, and it'll be only working with this. That's the damage tolerant approach. So if you say, I'm going to have a crack to begin with, you're not so concerned about the time it takes to start your crack in this kind of framework. You just say, I have one to begin with. I don't want it to grow more than a certain amount. So we call it a damage tolerant approach. But so going back to this example, when I have data, say I'm doing it twice here, well, I should just add it on. So I'm going to call it the aluminum 1, and then I have the aluminum 2. Hey, looks good, doesn't it? It's a higher curve. No problem. Now, if this didn't come from a single data point, and that's where the real business starts. So if this one came out and for a given stress level, I had a failure. There's really nothing interesting here. Just smaller stuff. So I had a failure here, another there, another there, and another there. And that was my typical curve. And that's something I want to introduce to you today. The other came out saying we were at higher stress. And yes, we ended up further. But say we had some kind of variation like this. And we don't really know why for now. But we had it. So it was more distributed this way. Now, qualitatively, this is not as good. You have too much variation. You have too much range in your levels that it's possible, say I take the worst case scenario here, so my curve would be something like this. I'm more or less showing that it could go under when you take into account the variability. And that's one of the things that we were looking at here. It's the same type of plot. We have two colors, we have two materials, and the dotted lines are what we call the confidence intervals. They are very helpful for fatigue, and hey, whether you take them into account or not in your design makes a huge difference. If I'm going to come here and say, well, this curve looks really good, you know, maybe 10 to the 7th cycle, 25 KSI, that's what I can take. If you take into account the risk of variation from your measurements, you'll be down to 18. So if you say it's 18 and the other is 17, well, now we have a change. It's different from one to the other. And that's really one thing I'd like you to take out is we don't take, in aerospace, you don't take these curves for granted. You have to go a step further and look at how they were generated and the variability that's associated with them. And when we talk about the landing gear having a safety factor of 1.1, 1.2, it's because they've already knocked it down based on actual data. So they went with more testing than you'll do in building up a trailer, just to be able to know that their safety factor is just 10% or whatever. So think about the effect of time and try to think about that the risk would be different depending on your application. And once you've figured out those two factors, you probably come back to me and say, well, my safety factor is actually pretty low. And a lot of it is based on history. So we came down and trying to just go back, here's the load. Oh, I don't really know my material properties in this case. And that's why I have to be consistent in my design approach so I can develop that industry history on failure rates. The casting factor of safety, we'll just go to it next class. Tomorrow, Professor Eager is going to be lecturing, and somebody is going to do something for you guys on Thursday.